onto both those leaves. And the leaves separate, exactly. So what I'm going to do is I'm going to take some rubber and my rabbit fur. Squeak, 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 squeak. Squeak, 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 squeak. Squeak, 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 squeak. And I'm charging by friction. So what charge is the rubber rod getting?
Negative.
Did you look at your notes?
It's gaining electrons.
It's gaining electrons, exactly. So rubber rod is becoming negative, and the fur is becoming positive. Are you seeing this?
Whoa.
So my rubber rod is what charge?
Negative.
Negative. So what are the negative charges doing? Are they going up or going down? They're going down. And positives are going up.
If you were to touch it, would it just lose all charge?
So if I was to touch the electroscope, the positives that were down here, the positives that were up here would go into the rod, and it would get super negative. Did anybody hear that? That snap?
Yeah.
Yeah, that's a pretty decent amount. So what then I need to do is, I lost the leaf. Then I would ground it. So I would ground it by touching something metal. So let's try this one again. A little bit. So let's make our rod negative. Boop, 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 boop. Okay, now, there we go. Okay, get out of there. Get out of there. Stop it. Stop it. Stop it. Oh, there we go.
Those look like a pain to deal with.
Which is why we're not doing this lab this year. They are a serious pain. But anyway, so yeah, so that's the point, is you can charge by contact by touching the charged object to the globe, or you can charge by induction. One common, this one I've already lost its leaf. One common exercise is if you brought a negatively charged rod to an electroscope and then touched the globe but didn't touch the rod, what charge is it now? Nope. So if I bring a negatively charged rod to the electroscope,
Don't you act as a ground?
yes,
Yourself?
I'm going to act as a ground.
Oh, it's the thing.
So the negatives, this is negatively charged, so the negatives are where? Charles, where are the negatives? On my phone. So if this is a negative rod, where do the negatives go?
Down.
Thank you, down. So if I touch the rod, I grounded what charge? The positives. So when I remove my finger, it gets a negative charge.
Oh.
Does that make sense? That's charging by induction. So I'm like, okay, rod is negative. Boop. I touch it, and I ground. You can barely see it because they're bent. So rod is negative. The negatives go down. I ground the positives, and now it is a negatively charged electroscope. Now it's a negatively charged object. Does that make sense?
Yeah.
Positives went up, negatives went down. I grounded the positives, leaving the entire thing negative. Cool?
Okay.
Maybe one of these days we'll get electroscopes that don't suck, but I've tried and failed numerous times. This is a different kind of electroscope. You can actually see, turn the light back off. You can actually see the animation. This is called a quantitative electroscope, meaning you're supposed to be able to measure the actual charge on the electroscope. I bought 10 of these at a considerable expense at the last school I was at, and they all sucked. So I decided I'm not going to buy those again. But you get the idea. So negatively charged, positives come up, negatives go down, the leads move. In this case, they ground the bottom, so the negatives went, and then when both the charging object and the device were removed, it had a positive charge. Make sense? Okay. Does this logic make sense to you?
Yeah.
Because I don't want to do this in a lab, but you need to understand this. Okay, should we move on? Hey, last night there was lightning! Woohoo! So where does lightning come from?
The sky. God.
Zeus. Zeus is like got his lightning bolt. Zeus. God, like I hate that guy in particular. So lightning requires clouds, right? Now, this is actually still pretty new science. So if I was teaching this about 10 years ago, I'm like, the current theory is, and we're not sure. Now I can say, the current theory is, and we're pretty sure, that how it works is friction and air from water and ice molecules, which are more dense than the rest of the cloud, falling through the cloud creates a charging by friction issue.
Oh, because when it rains.
Yeah.
Okay.
So that's the current, and it doesn't even have to rain. It's just the rain doesn't actually make it to the ground. It's just as ice crystals and water crystals fall through the clouds, we get a charging by friction issue. And what happens is the cloud charge separates, with the top of the cloud being negative, and the top of the cloud being positive, and the bottom of the cloud being negative.
Wait, so
Yes.
why is it that a lot of the time whenever you see a lightning bolt like slow down, it looks like it starts from the ground?
Because it's fast.
It doesn't have to. I don't know. I can't address that.
It's
Again, it's all about electrons moving, and electrons can move in however they want. But so this is again, this is the current theory. It could be opposite. Maybe the bottom is charged positive and the top is charged negative, and the Earth becomes charged negative. Just, last time I did the research a few years ago, this is what happened. So the cloud gets charged polarized. The negative is down below, the positive is up top. That causes the ground to be positively charged, and eventually when the charges are large enough to breach the insulator that is the air, then you get a lightning strike. So when the charges are strong enough between you and the doorknob, that's when you zap yourself. Or you and your car, that's when you zap yourself, when the charges are high enough. You know how to keep yourself from getting zapped when you get in or out of your car? Just touch
You
something
don't
metal.
drive or get your
Don't-
driver's license?
Yeah, you just drive a moped. No, touch something metal as you get out of your car or get in your car. That way the charges are constantly getting dumped back into the car. If you only touch something plastic, you'll hold on to all those charges and you're like, zap,
Wait.
darn it. Yeah.
What about touching wood? Because in 8th grade we learned that was like the best way.
Touching wood?
Yeah, like,
No, wood is an excellent insulator.
okay, so that is like, if you're trying to get rid of a charge.
Yeah, metal. Yeah, wood's a good insulator. You don't want to use wood to get rid of charge.
Don't?
Do not. And the best insulator is plumbing, because plumbing is in the ground. Did you know plumbing is in the ground? So the best place to ground yourself to get rid of your charges is plumbing. Just touch something plumbing. Okay, questions? We're gonna whip out the Boulder graph a little bit later. But first, some math. Coulomb's law. Coulomb's law has a direct analog to Newton's law of universal gravity. Okay. So Coulomb's basically says an electrostatic force, which could be attractive or repulsive, depending on the sign of force, varies with the charges of the objects and inversely with the distance between their centers. Now, if you remember universal gravity is always what? Attractive or repulsive? Hang in there, Scott. Hang in there. Dave. Gravity is always what? Attractive. So, which is why Rome is attracted to Spencer. Any object with mass is attracted with any object with mass. So gravity is always attractive. Electrostatic force could be attractive or repulsive depending upon the sign of F. Now, first of all, the charge of an object is measured in coulombs. Coulombs is the charge in, pay attention to this chemistry AP, 6.25 times 10 to the 18th electrons.
Oh, this is that. I hate.
Yeah.
I don't like
So,
stoichiometry.
Yes, stoichiometry of charges is what to do. So,
This is so gay. I don't like it.
oh, yes, this is chemistry AP last year. I hated electrochem. You'll love electrochem. Electrochem's pretty cool. Because anyway, I'll stop right there. So a coulomb is the charge in 6.25 times 10 to the 18th electrons, and this is where we get Faraday's law. Hint, hint. We have mold electrons, but that's how many electrons we have. A coulomb is the standard unit of charge. So this is our formula. Force, electrostatic force, is equal to the Coulomb constant, which is actually one of the easiest ones to remember. The Coulomb constant is 9e9. 9 times 10 to the 9th. Easiest constant to remember ever. 9e9. Charge of object 1, charge of object 2, divided by the square of the distances between them. And again, we're talking about very small charges. So you're going to get really friendly with your exponent key again. Times 10 to the negative 12, times 10 to the negative 13,
Oh, boy.
times 10 to the negative 6. We use millicoulombs, we use microcoulombs and nanocoulombs. So yeah, get comfortable with your exponent key. If you remember, milli, 10 to the negative 3, micro, then, let's try that again. Milli is 10 to the negative 3, micro is 10 to the negative scribble, 10 to the negative 6, and nano is 10 to the negative 9. So get really friendly with your exponent key in this unit. F equals, so the force, electrostatic force, is equal to the Coulomb constant, which is 9 times 10 to the 9th, multiplied by the charge of object 1, multiplied by the charge of object 2, divided by the square of 8 in between them. That's the electrostatic force. Now, if your F is positive, is it attractive or repulsive? Are you just guessing or thinking about it?
So the
Think
F
about it.
positive.
Take 30 seconds, and if you return an F that is positive, is that an attractive force or a repulsive
Proton
force?
force. I'm gonna say
So,
attractive.
I'm just guessing here,
Positive.
Don't just guess.
but I'm just gonna say that,
Don't just be.
negative.
Don't just guess. I take no responsibility for my education.
Yeah.
100%.
D squared.
My education is something that just happens to me. I'm not taking any responsibility for it.
But then
All right. If you think a
Like-
positive force is attractive, do this. If you think a positive force is repulsive, do this. Repulsive, repulsive, attractive, repulsive, attractive, repulsive, repulsive.
I'll be the minority.
Attractive, repulsive, repulsive, repulsive. Don't know on his phone, repulsive, and asleep. Okay, so if your F is positive, that means your Q are both positive or both negative. A positive F is repulsive. Okay? A positive F is repulsive. If you have a negative F, that means one of your Q's is of the opposite sign, positive, negative, negative, positive. A negative Q is attractive. Capiche? All right.
Do you
Will you keep
want
it up there for a
negative
second?
Leaving up here for a second. It doesn't matter. I mean, it depends on what you want to do. The fact of the matter is, if you have a positive and a positive, that's going to return a positive F. That's going to be a repulsive force. If you have a negative and a negative, that's going to return a positive F. That's going to be a repulsive force. If you have a positive and negative, or a negative and a positive, that's going to return a negative F. That's going to be an attractive force.
Mr. Byers,
Yep.
does the universe favor positive or negative?
Doesn't either one.
Does the universe?
Are you talking about this or something in chemistry?
No,
Okay.
like free energy.
Oh.
Like G.
Universe favors a negative free energy. Universe wants the energy back. The universe loaned the stars all the energy when it was created, and it wants it back.
So when you're talking about like they give you the three options and it's like positive, negative, negative, it's the most negative one or like,
Yes.
Wait, but where is the energy
Okay.
gonna go?
So this is called a point charge, and the lines around the point charge are called field lines. Okay? This is called a point charge, and the lines around a point charge are called field lines. Field lines, by convention, are just a way for us to identify electric fields and visualize them. A negative point charge has field lines that point towards. You look at this in your concept crossword. So a negative point charge has field lines that point towards it. A positive point outward. So if you drop a point charge into, if you drop a sample charge into that point charge's electric field, that sample charge is going to feel a force equal to the quantity of Q1, the quantity of Q2, multiplied by 9E9, divided by the square of the distance between them. Yes.
So I have a question. You know how they like split atoms during like, World War II?
Okay.
Did they use any like electron, proton stuff, or is that something completely different?
No, absolutely. Yeah, they would isolate a single proton and hold it in either a magnetic or electric field, and then fire it into the magnetic chamber that spun it around and around and around and around. Yes,
And that's how they do.
very common.
And that's how
Yeah,
you make
blew up
nuclear
everything.
bomb.
That's how you do it. Okay, 2 minutes left. So let's just talk about point charges, then we can call it a day. So Again, point charges produce electric fields around them. Just like a point of mass will create a gravitational field around it, a point charge creates an electric field around it. So positive charges have fields that radiate outward. Negative charges have fields that radiate inward.
Okay.
Now, just like a point mass creates a gravitational field, a point charge creates an electric field, and when you put a force or put a point mass in a gravitational field, it feels a weight. When you put a point charge in an electric field, it feels an electric strength. Okay. Just like when you put a point charge, a point mass, Fg equals mg, Fe equals QE. Mass, charge, force, gravitational field, magnetic field, or just electric field. Make sense?
Wait.
Okay.
So M is mass, Q is the charge.
M is mass, Q is a charge.
Okay.
Yep. Gravitational force, gravitational field, electric field.
And that's only for one object, right?
Correct. Yeah. One point thing in a field. Okay. And we're going to develop this equation and tack a few things on it in a little bit. But does that make sense, first of all? What's the unit of field charge? Or what is the unit of field strength? This is a Newton. Okay. We'll come back to this tomorrow.
Sick, bro.
Sick, bro. Don't be sick, bro.
It's Friday. We're gonna Monday.
We will visit this